Hello, everyone. This work is joined with Santiago, Balseiro, Omar, Besbes, and Bolun. And as the title suggests, we are looking at strategic behavior of batteries. Why is that? The electric grid in California and throughout the world are undergoing a transition with the rise of renewables. You can see here this graphics from the New York Times that shows the different types of generation throughout the day. You can see like the different types of generation. They are roughly constant, except solar, that is like a big bulge in the middle of the day. But the issue with solar is that as nice as it is, it only produces energy when the sun shines, which might not necessarily when you want it. Batteries are a natural complement to this because you can actually control the batteries and they can shift energy from when it is produced to when it is needed. And you can see here the dramatic rise of battery capacity just in the last few years from almost nothing in 2021 through like basically 25% of peak demand today. The issue is that these batteries, they look like this. They are specially built grid scale, utility scale battery storage facilities. They are really big relative to the local grid, and they are also built by big companies like Tesla. And so because they are so big, regulators are starting to be concerned about the potential for them to distort the markets around them. For example, the California's regulators launched a so-called storage default energy bid initiative, where they say in their reports that none of these storage resources are currently subject to market power mitigation, and the regulator believes that it is important to develop mitigation measures to manage market power, given the rapidly growing number and influence of energy storage resources. They also wrote a special report that identified unusual behavior of batteries that don't specifically call out market power, but we can show later that this is a consequence that can be rationalized by batteries' market power. When we say that the battery has market power, what do we really mean? These batteries are private entities like Teslas or people who buy like batteries from them, and they're trying to making profit by trying to lock in the price gap between the peak and the off-peak. The issue is that the price is determined not really by the total system demand, but by the net demand, which is basically the component of the demand minus the renewables like winds and solar. And this is because the wind and solar have basically zero marginal cost. And you can see here like that the low price is during the off peak in the middle of the day because there's a lot of solar and because there are more and more solar each year, the off peak prices are going down and down while the peak price stays up because that's when the sun sets and there is no more sun. So this leads to like a deepening ramp that solar requires. This is called a duck curve because it looks like a duck. Even though the duck is cute, it is not very nice for the grid because you need more and more like expensive and like polluting like fast burning gas plants, which negate part of the benefits of having renewables in the first place, both in terms of cost and in terms of carbon emissions. Batteries are supposed to help with this because they can shift energy from off-peak to peak, taking advantage of the price gap between them and also reducing the system costs. But these are not necessarily the same, which motivates our question, which is that like, given that these are like profit-making entities, how aligned are they with the system goal? More precisely, firstly, we want to identify, given the stochastic and changing randomness in electricity markets, how do batteries decide how to charge and discharge? And how does this strategic behavior of decentralized profit maximizing batteries distort decisions compared to centralized batteries? And what is the impact of this on system performance? So what are the features about electricity markets that we want to capture? First is that it clears in two stages. We have the day-ahead market, which is cleared like 1 day ahead of time, mostly based on the forecast because nothing has happened yet. This is useful because it reduces uncertainty for market participants. But even more importantly for us, it allows slow generators like coal plants that need several hours to start up advance notice to produce. And this is just a purely financial market. In contrast to the real-time market, which is when energy actually change hands based on the realized demand, such that demand has to equal supply at all times. Otherwise, you have blackouts, and we really don't want that. And this is both a financial market and a physical market. We can now put like numbers or variables into this. This is our model where you have two periods, the peak and the off-peak, corresponding to the two parts of the duck curve that we have seen before, and the day ahead and the real time. So basically, we have four things. We have day ahead peak, day ahead off peak, real time peak, and real time off peak. That where you want to clear the expectation, which is the forecast of demand in day ahead, and the actual realized random variable in real time. And the key player is the battery, which is strategic. This is like what we mean when we say that we want to see how the battery behaves, because the battery decides how much to charge and how much to discharge, which is just a scalar variables in day ahead, but are policies in real time, subject to the constraints that the amount that you are charging must be equal to the amount that you are discharging, because the battery doesn't produce energy, just shifts it around. And you can extend this to multiple periods. Here you just show the two periods where you are like drawn from a joint distribution so that you capture the randomness within each period as well as the correlation across periods. And the market power is reflected when you have these decisions of charging and discharging that are affecting the prices. And if you are like just a central planner, you don't really care about prices per se, you only care about total system cost. But as a profit maximizer, you care about the prices because that's where you're making your profit. And the prices are determined basically by supply and demand, with the twist that because we have the slow and the fast generators, the slow generators do not change from day ahead to real time. As you can see here, you have the supply from slow plus fast generators equals the demand that you need, where the slow generators don't change, so only the fast generators can change, as well as the real time and adjusting the real-time price with it. And so this tells you implicitly what the prices should be. And as we have alluded to before, we want to look at what batteries behave. In the no battery case, this is just a benchmark, as well as when you are minimizing generation costs versus maximizing battery profit, which we can show that there are solutions to convex infinite dimensional optimization problems. You can solve them explicitly. The actual formulas do not matter as much, only that you can read out that the centralized ideal case differs from the decentralized one in three different ways, which we can show intuitively like this. The first one is quantity withholding, where you are not charging and discharging as much as you should. As you can see here in in purple, where the charging is higher than the decentralized, because when you are charging and you are discharging, the price impact like reduces the price gap. So you have to trade off between price and quantity. The second one is that you are hiding some of your capacity in day ahead and only makes it available later in real time, leading to temporal misallocation. As you can see here in blue, from 0 in centralized to something in decentralized. And lastly, that you are less responsive in real time, as you can see in red, by like not smoothing the deviations from forecast as much as you should. So these are the types of things that are suboptimal from the central planner's perspective. But how costly is this? You can quantify this by defining the price of anarchy metric by looking at how much cost reduction you can get in an ideal centralized case versus divided by the decentralized case. This ratio is the price of anarchy, which is always greater than 1. And the closer to 1, or the lower the price of anarchy is, the better the incentive alignment. You can show that this price of anarchy is both like bounded below by 9/8 and bounded above by 4/3, meaning that the incentive alignment, misalignment is always there, at least 12.5%. But importantly, even in the worst case, it never exceeds 4/3 or 33% misalignment. And remember that we have been assuming worst case things so far. So you have like a monopoly battery that is perfectly efficient, and that has like as much capacity as it needs. And even then, battery market power is bounded even in the worst case. If you have competition, say N batteries, you find that the price of anarchy actually is even smaller, goes down at a rate of 1/n². Which means that competition is very effective at aligning incentives, with the caveat that the profit is reduced, which might actually discourage entry. This basically means that the takeaway is that the market power might not be as big of a deal as the regulators might have thought, at least at a macro scale. And we should be encouraging more battery entry into the market over like fine-grained regulation at a nascent stage. And these insights continue to hold under various realistic extensions, as well as we have calibration with real data from California and Texas. So these are the takeaways. We have an analytical model. We show distortions. We show the loss from market power is bounded, and that competition is good. Thank you. For a couple of questions.
So, for example, thanks for the talk. If you would need to expand, for example, the power of the market, who do you think should be paying for it? If you want to expand the power of the market, who do you think should be paying for it?
Yeah, so I think the question is, if you want to expand the power in the market, like what would you do? So this is not directly modeled here, but like one of the main real world obstacles is interconnection, which is that it takes a really long time for resources, whether there are grid scale batteries or like solar farms, wind farms, everything to connect to the grid. Hey, okay. So one of the main real world obstacles for getting more power into the grid is the interconnection, meaning that like it takes a really long time to do like the studies, both like technical studies as well as like the community engagement needed to connect like battery farms or solar farms or wind farms or any type of generation into the grid, both on the technical side as well as like engaging the community and the like environmental regulations needed. And this has become even more like severe when you have like a big growth in say like AI data centers. There is a lot of startups as well as a lot of community efforts trying to alleviate this, but it is still a work in progress.
Okay, I think we're actually going to take all further questions offline. So let's thank Jerry again and thank all the speakers again.